In this chapter, we will discuss lateral earth pressures on structures such as retaining walls, sheet piles and braced excavations. We will focus mainly on Rankine's theory, which is simpler than Coulomb's and hence widely used in designs. So far, we have looked at ways of determining vertical overburden stresses. The horizontal stresses in soils are quite different to the vertical stresses. Here are some geotechnical applications where it is necessary to know the lateral earth pressures. Let's discuss three special cases: at rest, active, and passive states in the soil. Most of the time in designs, we assume one of these three states for computing the lateral earth pressures. The three states are in fact defined by how the soil deforms laterally. At rest state implies the soil does not undergo any lateral strain. It is a very stable state. When the soil is allowed to expand laterally, it fails at active state. When the soil is compressed laterally, it fails at passive state. Note that the soil fails at active and passive states, but in different ways. In the homogeneous soil mass shown here, where the ground surface is horizontal, the ratio of effective horizontal stress to effective vertical stress is a constant which is called the coefficient of earth pressure at rest, denoted by K0. It is the same at all points within the homogeneous soil mass. Here, you can see three different soils in a soil profile, with their specific K0 values. Once the effective vertical stress is determined at a point, the effective horizontal stress can be determined by simply multiplying with the K0 value. For normally consolidated soils, K0 is typically in the range of 0.4 to 0.6. Assuming soil is an elastic continuum, it can be shown that K0 is equal to Poisson's ratio on 1 minus Poisson's ratio. There are also few empirical equations to estimate K0. First, you find the effective vertical stress at A, sigma V dash. Multiplying this by K0 of 0.52 gives the effective horizontal stress sigma H dash. Adding the pore water pressure to this, gives the total horizontal stress at A. Here, first thing is to plot the variation of the total horizontal stress sigma H with depth. To do this, determine the sigma H values at A, B, C, and D. Divide the plot into triangles and rectangles to compute the magnitude and location of the resultant force on the wall. Let's understand the difference between active and passive states. The smooth wall OA retains a granular backfill which is initially at rest, that is, K0 state. When the wall moves away from the soil is allowed to expand laterally and finally it fails. The failure state is called active state. When the wall is pushed toward the soil is compressed laterally until it fails. The failure state is called the passive state. While the wall moves, the horizontal stress decreases or increases depending on the direction of the wall movement. However, the vertical stress remains the same throughout. The soil failure discussed herein, at active or passive state, happens at every point within the soil mass. We will show that the failure planes in active state are inclined at an angle of 45 plus half phi to the horizontal. In passive state, the failure planes are inclined at 45 minus half phi to the horizontal. Here, a smooth vertical wall retains a granular soil. Initially the soil is at rest, and hence sigma H dash on sigma V dash is equal to K0. The red line shows what happens to the effective horizontal stress when the wall is pushed towards the soil. The blue line shows what happens to the effective horizontal stress when the wall is allowed to move away from the soil. The failure values at active and passive states are denoted by sigma A dash and sigma P dash, respectively. The soil is initially at rest. The corresponding Moore's circle is shown in dashes. As the wall moves away, sigma H dash decreases, and sigma V dash stays the same at gamma times the depth. The Moore's circle expands from the left, and when it touches the failure envelope, the soil fails. That happens at active state. Let's have a good look at the Moore's circle at failure. Here, sigma A dash is the effective horizontal earth pressure at the active state. We can show that sigma A dash is equal to a constant Ka times sigma V dash. The constant Ka is called Rankine's coefficient of active earth pressure. Here, we use the Moore's circle fundamentals to determine the orientation of the failure plane, represented by the point F. It is shown that the failure plane is oriented at half of 90 plus phi to the horizontal, which is 45 plus half phi. When there is cohesion, with C' not equal to 0, the expression for sigma A' has an additional component, minus 2C' square root of Ka. The expression for Ka is still the same as for granular soils. Ka has an alternate expression given by tan squared 45 minus half phi, which is the same as 1 minus sine phi on 1 plus sine phi. Here, we discuss the passive state with granular soil. When the wall is pushed towards the soil, the horizontal effective stress increases from the initial at rest state. When the Morse circle expands on the right and touches the failure envelope, the soil reaches the passive state and fails. During the wall movement, sigma V' remains the same. From trigonometry, we can show that sigma p' equals a constant Kp times sigma V'. Kp is Rankine's passive earth pressure coefficient. From the Morse circle fundamentals, we show that the failure plane, defined by point F, is inclined at 45 minus half phi to the horizontal. When there is cohesion, we have an extra term in the expression for sigma p'. We have an alternate expression for Kp, which is tan squared 45 plus half phi, same as 1 plus sine phi on 1 minus sine phi. The lateral earth pressure variation with depth is linear for active and passive states in granular soils, passing through the origin. The resultant force on the wall acts at the centroid, which is at 1/3 h from the bottom. In cohesive soils, the topmost region of the clay is in tension, as you can infer from the expression for sigma A'. This region may have tension cracks and therefore, we will neglect this region in determining the active load on the wall. That is a conservative approach, not relying on the tensile stresses. Rankine's earth pressure equations for active and passive states we discussed till now assume that the ground level of the backfill is horizontal. When it is inclined at beta as shown here, the expressions for Ka and Kp are different.